What's up, y'all? I'm Bielkiewicz, and I'm the Group 1 leader for Experiment 2 next week, the bomb calorimeter. So basically, we've got the slide, but more or less what this experiment is doing is it's measuring the heat of combustion for engines, and not an actual engine, but we're learning about the heat of combustion, thermal capacitance, and things like that when oxygen is enclosed in a specific volume. And this is important because, I mean, engines, anything that use an internal combustion engine, this is what's going to be used. And like I said, there's solid and liquid samples, and it's a standardized way to actually measure the heat of combustion. So objectives, it's more or less just becoming familiar with the heat of combustion, as I already talked about, and thermal capacitance. And I'm going to get into what those mean in a little bit. So heat of combustion is number of heat units liberated by a unit mass of substance plus oxygen in an enclosed area. So this relates to obviously a car because the combustion chamber is your fuel and oxygen with your spark plug, which ignites, which basically turns the whole system. So this obviously relates because every car that's being used right now is using an internal combustion engine, and it's the only real efficient, durable way to power vehicles. Like I said, when ignited, the heat is transferred from the actual bomb surface to the surrounding yada yada. So Q, before I get into the actual equations, given some definitions, Q is the heat of combustion. MCV is the thermal capacitance, with M being the mass and CV being the specific heat, meaning the heat per unit of mass. And then the delta T is the change in temperature of the system. So the three equations used is, it's based upon the first one of thermo. Q equals mass times CV times delta T, so thermal capacitance times the change in temperature. And this can obviously be manipulated into go whatever form of the equation you want. If you want to put it in terms of thermal capacitance or delta T, whatever form you want to put it in, you can. And like you have heat, thermal capacitance, heat of combustion with the known fuel. Yeah. So the actual apparatus of the system, as shown, number one, we have the igniter, which is shown in detail here, which I don't have the actual specifications of what each label represents, but more or less the igniter is going to ignite the system to actually start the process of combustion. Number two is the actual bomb. 3 is where it connects to the laptop. 4, which at 3 and 4 isn't shown, but it's a laptop, and then how it converts that signal to a digital signal. 5 is the actual bucket, which holds water and the bomb in it. 6 is the thermocouple, as shown up there, which is also connected to that DAC computer sensor, and it's used to measure the temperature increase. And then 7 is the water stir motor, and the water stir motor is important because it continually keeps the water moving and running, so you don't get a different temperature or different reading at one location as compared to another. It keeps it fluid to where it's constant throughout. So going into the procedure, starting with the bomb preparation, you have your benzoic acid and you put that into the crucible as shown before. What you're going to do next is put on the ignition wire to the electrodes of the bomb, add the distilled water, pressurize and depressurize, and go on with that process. You want to prepare the water jacket next. As you can see, put the water in the bucket. 3, instrumentation. So as I already talked about, you want to make sure the computer's set up with the right DAC view to where it's showing the right results that you want to get. And you want to put the thermocouple into the correct slot. You want to position it and then wait 2 minutes before data, because you don't want it to be any, I guess it could introduce error into the measurement if you're not going to wait 2 minutes. So you want to wait before it's stable to where you can actually get data that would work and make sense. And then the actual experiment, after you waited the 2 minutes, you want to ignite it. And basically, it's already what we talked about. The ignition happens, it's all going to combust. You're gonna find out your heat of combustion and all this other data that I'm gonna talk about with my predicted results just in a second. Shutdown procedure, turn off the motor first, make sure it stops running. You're gonna clean up your area, and just the regular thing of safety. So lastly, we had to find what the thermal capacitance of the whole thing. So you do it, this is predicted experimental results. With water and stainless steel, you find them with the formulas, and then you add them up, which is this. And this kind of makes sense. So this thermal capacitance would be kilojoules per degree Celsius. So what this realistically means is how much energy is lost or gained per degree temperature. So in this case, 9.864 amount of energy is gained per unit temperature, meaning the combustion is obviously efficient doing its job because it's producing energy. And then next we had to do the delta temperature for 1 gram of benzoic acid, which I found to be 2.67 degrees Celsius, which again goes in with the experiment using the benzoic acid. And then sources of error could possibly not waiting the 2 minutes before your measurement. It could be not giving the system enough time to reach equilibrium. And then lastly, not following the right procedure and shutting down and cleaning up the system and things like that. Here are my sources. So, thank you.